Welcome back to another week of geometry. And today what we're going to do is we're going to do a warm-up problem that involves solving some application problems involving right triangles and trigonometry. So to begin with both of these problems, there's two separate ones. What we need to do is we need to draw a picture for both situations. So read through both of them, draw a picture, and see what you can come up with using right triangle trigonometry. And as a reminder, we're going to be using sine of theta equal the opposite over the hypotenuse. We're going to be using cosine of a certain angle, which is going to be equal to the adjacent leg over the hypotenuse. And then you're also possibly going to be using the tangent ratio, which again is the opposite over the adjacent side. So give these two a whirl, and let's see how we do. Alright, let's take a look at how we did on the first problem. Again, important to draw a picture. So this is the picture that I drew. We have a 42-degree angle. Here's Alejandro standing there. He's 140 feet from the base of the building. I don't know this height. So I use the tangent ratio because I don't know the opposite side, but I do know the adjacent side. So I set up this ratio of tangent 42 equals the opposite over the adjacent, cross multiplied, and I got 126.06 for the height x. But remember, his eyes are 6 feet above the ground, so I had to add 6 feet to my answer. And when I did that, I got that way over here as 132.06 feet because I had to add 6 to this answer that I have right there. So altogether 132.06. Now on the second problem, an 18-foot ladder, so this slanted height is 18 feet, that's the height of the ladder, is resting against a wall, and it's 8 feet from the base, so what's the angle that it's making? Well, in this case, I have the adjacent leg, and I have the hypotenuse of this right triangle. That would be the cosine ratio. So as I solve for the cosine ratio, I end up taking the inverse cosine. Remember, when you're finding an angle measurement, that's when we do this cosine with a little -1, which is the inverse cosine of both sides. That undoes the cosine ratio, or the cosine operation, and so then I'm left with my angle, after I type that in my calculator, of 63.61 degrees. Alright, what we're going to do today is we're going to talk about special right triangles. And there's two kinds of special right triangles that we're going to study, and what we mean by that is there's two dimensions of triangles, or two different kinds of angles with measurements that we're going to study. And I'm going to deviate a little bit from the textbook on this, but just so you know where it's coming from. But the first kind of triangle that we're going to examine is something called a 30, 60, 90 right triangle. And what this 30, 60, 90 triangle looks like is a triangle that looks like this, where this is the 90 degrees down here, here's a 60 degree, and here's a 30 degree angle. And the reason that we like these is because they give us some shortcuts to be able to find missing side lengths within certain triangles. So the relationship with all of this is that if I know that this length right here, I'll call this length x, if I don't know what that is, in a 30, 60, 90 triangle, the side length that is across from the 30 degrees, this is referred to as the short leg, as that is going to be the shortest leg within a 30, 60, 90 triangle. The short leg is always half the length of the hypotenuse. So whatever I know the hypotenuse is, I just take half of that. So in this instance, that would be 1/2 x. Okay? This leg right here, across from the 60 degrees, that's called the long leg. And the length of the long leg in a 30, 60, 90 triangle is always taking whatever the short leg is times the square root of 3. So that's pretty sweet. The reason that we use these is it just allows us to find exact values very quickly in a 30, 60, 90 triangle in order to help determine some missing side lengths. So in our specific problem here, if I have 1/2 x for the short leg, so if I did 1/2 x and I multiply that times the square root of 3, what that's going to make for this specific problem is square root of 3 over 2 times x. So if I just knew one of these lengths, I could find the other two by using these relationships in a 30, 60, 90 triangle, and I'll show you what that looks like here in a little bit. But the other kind of special right triangle that we're going to be looking at is something called a 45-45-90 triangle. And so a 45-45-90 triangle is exactly what it sounds like. It's an isosceles triangle with two 45-degree angles. And so that would be here and here. And so if I have this length here, x, I know that this length right here will also have to be x. These two lengths in a 45-45-90 triangle have to be the exact same. And the reason being is because it's an isosceles triangle. Now you could use the Pythagorean theorem in order to help you determine what that missing length of the hypotenuse is. But in a 45-45-90 triangle, the hypotenuse is always going to be whatever one of the legs is multiplied by the square root of 2. So in our specific problem, it would be x times the square root of 2. Or you could say the square root of 2 times x, either way. But let's say that a leg was 7. Well, then the hypotenuse of my triangle is going to be 7 times the square root of 2. And so it just provides a shortcut for us to be able to determine a missing side length without having to do a lot of extra work if you can understand these ratios or relationships in a 30-60-90 or a 45-45-90 triangle. And so what we're going to do is we're going to skip ahead a little bit in some of the problems to practice them and just see how we can use these to help us find missing side lengths. Alright, I'll walk through a few problems here just to see if we can come up with some conclusions. So what we're looking at in part A, it says use your new 30-60-90 and 45-45-90 triangle patterns to quickly find the lengths of missing sides. So in part A of number 50 here, in the past what we would have to do is use SOHCAHTOA, or we'd have to use sine, cosine, or tangent. But now hopefully you can recognize that this first one in part A is a 30-60-90 triangle. This would be the short leg, obviously because it looks the shortest, but it's also across from the 30-degree angle. So if you remember what we talked about in the first slide that we just did, this is the short leg. Well, that's always half the hypotenuse. So that means the hypotenuse has to be 20 units. And in order then to get the long leg, this leg here, we said you take whatever the short leg is and you multiply it by the square root of 3. And so that means that this length is going to be 10 times the square root of 3. And you can just leave your answer like that. You don't need to multiply them together. So that's how I can use a 30-60-90 triangle relationship in order to help me determine some missing side lengths. And I would continue on part B here as well. You should recognize that this is a 45-45-90 triangle, so that's also a 45-degree angle down there. Since that's a 45-45-90, I know that both these side lengths have to be the same, so they're 4. And then in order to get the side length, or the hypotenuse in a 45-45-90, what we said is you take whatever the leg is times the square root of 2. So that means that this length right here is going to be 4 times the square root of 2. And you can just leave your answer like that. That's no problem. Now in part C, working backwards, this is a 45-45-90 triangle. I know that both this leg and this leg have to be the exact same length. And so in order to go from leg to hypotenuse, we multiply by the square root of 2. But if you want to go from the hypotenuse back to one of the legs, what you do is you divide by the square root of 2. And so you can also think of it this way. Some number times the square root of 2 equals 8 times the square root of 2. And maybe you can recognize this already, but that length would have to be 8. 8 times the square root of 2 is going to be equal to 8 root 2. Or if you took this thing right here and you divided that by the square root of 2, essentially the square root of 2's cancel each other out, so that means both of these missing side lengths are going to be 8 in that 45-45-90 triangle. In this problem down here, it's a 30-60-90 triangle. Here's the 60 degrees, so that means that this length across from it is the long leg. And so remember, going from the short leg to the long leg, we multiply by the square root of 3. So to go backwards, we would have to divide by the square root of 3, which would mean 9 divided by the square root of 3, like that. So then in order to get the hypotenuse is always twice as long as the short leg. So I'm going to have to take this quantity and multiply it by 2 to get 18 divided by the square root of 3. And so those lengths hold up within that 30-60-90 triangle. One more problem here with a 30, 60, 90. If I have a 60-degree angle here, here's a 30-degree angle. So that means this length is the short leg. Remember, this is the hypotenuse. The short leg is always half of whatever the hypotenuse is. And then in order to get the long leg, I take whatever the short leg is times the square root of 3. That's just the rule that we have in a 30, 60, 90. So that means that this is going to be 3 times the square root of 3 for that specific problem. And then in letter F here, this is another 45, 45, 90 triangle. So if I know what the hypotenuse is, I actually divide by the square root of 2 to go backwards. So that's going to make 6 divided by the square root of 2. And so both the side lengths in this 45, 45, 90 are going to be the same length. So this is going to be 6 divided by the square root of 2 as well, as that's an isosceles triangle. That's all the work that we're going to do for today. It's just these special relationships of 45, 45, 90 and 30, 60, 90 triangles. Again, these are merely used to help us find shortcuts within right triangles, and we call these special right triangles. And so this is something that's going to continue to pop up later in your math classes as well. Hopefully all is well with you. If you do have questions, please do not hesitate to reach out. Stay safe and stay healthy.